Okay, one very important 2x2 table is when the data actually represent matched pairs of matched data. So for example, here we had a matching between two individuals and they were matched on age and sex. Okay, and they were at 288 individuals. But because of the matching, we shouldn't consider them as 288, but rather 2 times 144. Rather, consider them as 144 couples. And then for each couple, determine whether what their diabetes status was and what their myocardial infarction status was. So that's what the study was, to determine whether there's any relationship between diabetic status and myocardial infarction status. And this was done as a matched pair of studies. Okay, and the test we're going to look at is called McNemar's test. And this is a sort of a parallel. Remember when we did the t-test, we had the two samples, and then we said either the two samples are independent of each other or the two samples are dependent of each other, namely, for example, with the before and after. So you measure the same person twice, say before and after. Well, this is the analog with that. So here we're going to have 144 pairs. So if we look at the 144 pairs, we see that there are 9 pairs where they both had diabetes and 82 pairs where neither had diabetes, and this was amongst the MI and amongst those who did not have MI. So with those with no MI and diabetes versus MI and diabetes, there were 9 of those, and then with no diabetes, MI and no MI, there were 82 of those. And the argument is that if there's going to be a difference between those with MI and no MI and diabetic status, then it's the discordant pairs that we should be looking at, these 37 and these 16. And is it just as likely to be in this quadrant as this one? And that's what the McNemar test does. It tests the hypothesis that you're just as likely to be up here as down there if you're going to be a discordant pair. So in other words, is in very rough terms, is the difference between 16 and 37 attributable to pure chance, or is there something going on here? Now note, we ignore what's happening on the diagonal, and that's what some people don't like about this test, is that you could have a zillion on this diagonal and a zillion on this diagonal, and the McNemar test would give you the same answer because it ignores what's going on the diagonal and concentrates fully on the off diagonal. Anyway, let us look at this 37 and 16, and what the McNemar test does. It just considers those discordant pairs and then takes their difference and divides by their sum. Now, this is a little bit controversial, this continuity correction factor. Some people do it, some people don't. Stater doesn't do it. Anyway, so there it is, 37 minus 16, and then minus 1, yes, no, and then square that and divide by the sum of them. In this case, it comes out to be 7.55. And if we look at a chi-squared with 1 degree of freedom, so compare this with the chi-squared with 1 degree of freedom, and what we see is that the p-value is going to be between 0.001 and 0.01. The p-value is certainly less than 0.05. So it's less than 0.05. So we would reject the hypothesis of equality here. If we feed it to Stater, there it is, and they get 8.32 instead of 7.55. But qualitatively, it doesn't matter because the p-value is still less than 0.05. This is called the McNemar test.